It's Neil Breakwell is a member of our society, and he's going to be talking tonight about the Celestial Coordinates and Sidereal Time. So I hope you all enjoy this, because I'm going to, because I don't know anything about it. So I'll leave it with Neil. Do you want the lights on, Neil?
Yeah, probably. Well, let's see. Maybe the back ones. I've got the camera going tonight. It's not because I like to hear the sound of my own voice, but my better half would like to listen to us later on. So that's the reason for the camera. But don't worry, you're only on audio. It's just me that's on video, unfortunately. These introductory sessions, they are much more informal than the main meetings. So please feel free to interrupt me and ask questions at any time. I'd rather present 50 slides and have everybody understand everything than present 100 slides and leave you baffled. Okay, so legitimate questions also include, is it time to break for coffee yet?
Yeah.
Anything like that. So,
Is it time to break for
not quite yet, not quite yet. So I wonder if, when you've looked closely at star maps, you've noticed that in addition to the positions of the stars and the shapes of the familiar constellations, there are also grid lines and a number of numbers down the side, very much like we see on a map of the Earth. And tonight I'd like us to take a look at just what exactly these numbers mean, and also how very useful they can be in helping us to find our way around, find objects in the sky, and also to determine if a particular object can be seen on any given night and location on the Earth. So before we get into that, I think it's really important that we take a quick look at some familiar, perhaps to some of us, concepts of how the Earth moves through space and how we map the Earth. And as I say, it's really important that we understand these ideas before we go on to talking about mapping the sky as such. So let's have a look at the Earth then, the Earth's spin. As you probably know, we live on a world which is inclined at 23.5 degrees, which spins on its axis from west to east in a little less than 24 hours. Now that little less will become very important later on, and we'll understand a little bit more about why it's not exactly 24 hours, which is really key to understanding one of the things we're going to talk about tonight, sidereal time. So more of that later on. This axis of rotation we actually use as the basis of mapping the Earth. And as we'll just ask the question now, we just said that the Earth is inclined at 23.5 degrees. But you know, there's no up or down in space, so what am I talking about? 23.5 degrees relative to what? Well, the answer is something called the ecliptic, which some of you probably are familiar with the term. But again, let's just introduce that term and understand what it is. What is the ecliptic then? Well, the Earth, as you know, travels through space about once a year, and it makes an orbit of the Sun. And all the ecliptic is a word to describe the plane in which it orbits. So if we were to draw a line perpendicular to, by which I mean at right angles to the Earth's orbit, that 23.5 degrees is measured relative to that. So that's all we mean by the term the ecliptic. It's just the plane represented by the grid pattern in this picture, in which the Earth moves through space. The axis of rotation is inclined relative to that. The other thing to bear in mind is that this tilt of the Earth's axis is the reason we have seasons. Now, that direction of tilt stays the same throughout the year. So the Earth doesn't move and change its direction of the axis. That axis of spin is always pointing in the same direction. Hey guys. That's all right. So in June, the northern hemisphere is tilted toward the Sun. So that's in the far picture on that side there. So in June, it's light for a little longer each day in the northern hemisphere, and dark for a little longer each day in the southern hemisphere. So that point of the Earth's orbit corresponds to what we call the northern hemisphere's summer and the southern hemisphere's winter. I just want to put in bold letters at that point, because this is a mistake which a lot of people make. to bear in mind that summer and winter have nothing to do with the distance of the Earth from the Sun. It's entirely a result of this tilt. Brian's looking baffled. Have you got a question, Brian?
Eh?
You're looking very baffled.
No.
I thought if I baffled you yet, we'll proceed with you.
No, I'm still with you.
Good. We are going to get on to the main subject of mapping the sky very shortly.
No, it's all right.
You haven't missed anything, guys. We've just been talking about some basic concepts of how the Earth moves through space. And we've just spoken about its orbit around the Sun and defined a term called the ecliptic, which is just the plane of the Earth's orbit as it moves through space. So just carry on from that. In December, as maybe you'd expect, the situation's reversed in that the southern hemisphere is tilted toward the Sun now, and the northern hemisphere's winter, and the southern hemisphere's summer. And these points in the Earth's orbit where the axis is pointed directly toward the Sun in one hemisphere are called the solstices. June 21st is what we call the summer solstice in the northern hemisphere, or the June solstice to be generic, because obviously in the southern hemisphere that's the summer solstice. So December 21st is what we call the December solstice, the summer solstice in the southern hemisphere, and the winter solstice in the northern hemisphere. Now, between December and June, there are points in the Earth's orbit where the axial tilt is in the direction of travel, which is these points here and here. At those points that we call the equinoxes, the days and nights are of equal length. So we have March 21st corresponding to the northern spring, southern autumn, and September 21st corresponding to the northern autumn or southern spring. So that's just a few terms introduced. Here's another term that we need to clarify, which is the zodiac. Don't worry, you've not walked into an astrology meeting. This is a perfectly legitimate terminology in astronomy. And all it means is a set of constellations which the Sun, as viewed from the Earth, appears to move through as it goes around the Sun. So here's a simplified diagram, obviously not to scale, of the Sun and the Earth moving around it at various points in its orbit. And you can see that from the viewpoint of the Earth, as we look towards the Sun, the constellations that the Sun appears to be in vary throughout the year. The Sun appears to move through a set of constellations, which we call the zodiac. Actually, you don't see the Sun move through the constellations, because in the daytime, of course, we don't see the constellations. But if we could switch off the atmosphere, we would see the Sun against various constellations. And those constellations through which the Sun appears to move throughout the year are what we call the zodiac. Any questions so far? Even better. Here's a little animation which shows it a little bit better, hopefully, which is a stylized picture of the Earth with the constellations in the background. And you can see that it actually shows light in one direction. That's the direction where the Sun is. So in January, at the start of January, the Sun appears to be here in the constellation Sagittarius, as viewed from the Earth. So that time of year would be a good time to view constellations which are in the opposite direction, over there, because they're in the nighttime side of the sky. Whereas it's not a good time to view constellations which are on this side of the Sun, on this side of the Earth, because it's daylight at that time when they're visible in the sky. And we can just move this little slider through the year and see how, as the year progresses, the Sun goes through different constellations, as we've seen, as viewed from the Earth. So the constellations that are in a good position to view vary throughout the year. They're the ones that are on the opposite side of the Sun. The opposite side of the Earth to the Sun, I should say. Okay, let's just have a look at recap on how we map the Earth then, and then we'll move on to talking about how we map the sky. So terrestrial coordinates on the Earth. How do we map the Earth? We divide it up into a grid pattern using lines in different directions. First of all, we define lines of what we call latitude, which are simply lines drawn concentric with the axis of spin that we spoke about earlier. So these lines here are what we call lines of latitude, and we just measure them in degrees north or south of the equator, from 0 to 90. In a similar way, we draw lines of longitude which run at right angles to those lines. So we end up with a grid pattern of, which enables us to define the location of any point on the Earth. Now, in any grid system we need reference points, we need a zero reference point. The zero line of latitude is quite easy to define, it's just the equator, it's the one that's furthest from both of the poles. So this line round the middle we call 0 degrees of latitude. But what about the 0 longitude line? We need a reference for the 0 longitude line as well. Now that's a bit more arbitrary, we could define it anywhere. And we just happen to define a line which goes through Greenwich. So we have now our grid system with 0 degrees latitude defined around the middle, on the equator, and a 0 degrees line of longitude. As we said, the lines of latitude are measured in degrees north or south of the equator. The equator is 0 degrees, the North Pole is 90 degrees north, and the South Pole is 90 degrees south. Now, in terms of lines of longitude, here is our reference going through Greenwich, and we measure longitude lines in degrees east or west of Greenwich. So a point here will be some 10 or 15 degrees east of Greenwich, and a point here will be a certain number of degrees west of Greenwich. So that's our coordinate system for mapping the surface of the Earth. Here's this animation which enables us to look at how we move a point on the Earth. We can see the equator is, this is the latitude coordinate, measured north or south, and longitude, let's just spin the Earth around a bit, is measured west here and east when we go to places east of Greenwich. So here in Derby we're about 52, 53 degrees north. When Anthony goes up to Iceland, when's that, next year? January?
January.
He's going to be about 65 degrees north.
Yep.
So we won't quite see as many southern constellations, but there'll be more circumpolar constellations. Okay? So as you can see, we can reference any point on Earth with that grid system. So let's have a look at the sky then. Let's have a look at the actual way that we measure we map the sky with those definitions under our belt. Let's introduce a concept called the celestial sphere. Now, as we know, the Earth moves through space and it spins once on its axis every day and moves around the Sun. Long ago, people used to think that the Earth was the centre of all things and that actually everything in the sky moves around us. We know, of course, that that's not the case now, but it turns out that that view is a really useful way of helping us to map the sky. So, if all objects in the sky, you see, really were fixed to a rotating sphere, and the Earth was stationary, an observer on the Earth would see exactly the same thing as he sees in the real situation, where it's the Earth that's moving, and everything in space, which is, for duration of a human lifetime, pretty much fixed in position. By which I'm talking about the distant stars, of course. Planets, we know, move much more complex way throughout the year, so we don't generally map the positions of planets on star charts, except ones that are printed every year. If you buy a map of the sky, you won't see the planets marked on it unless it's one printed for a particular year or a particular month. If you buy a general map, it'll just have the distant stars on it. So this celestial sphere then, although the stars and the distant galaxies that we map are strewn through space in all directions, in much varying distances, greatly varying distances, we still imagine everything to be on the surface of a sphere where everything's at the same distance from us. And that doesn't really have an effect from the point of view of an observer on Earth, because all we're interested in mapping the sky is the direction of objects. So we're mapping the sky, we're mapping the direction of objects, not necessarily anything to do with their distance. So for mapping purposes, all the stars, nebulas and distant galaxies, no matter how distant, are pictured as being fixed to a single crystalline sphere that rotates around us. Here's a little graphic which is very interesting. It shows the familiar constellation of the Plow, sometimes called the Big Dipper, which has this familiar constellation in the sky as viewed from the Earth. But as we can see, the stars are actually at very different distances. So if we were to be able to spin around and look from different directions, we'd see that the distance from the Earth to the different stars in the Plow are quite wildly different. These two, for example, are very much further than the rest of them. But, and so when we're doing maps of the sky, we're not actually looking at distance, we're looking purely at direction. So this celestial sphere that we've said we're going to imagine being rotating around the Earth, because we're so very small compared to the Earth, this is the kind of view that we appear to have. We appear to be standing on a large flat disk with the celestial sphere touching the horizon in all directions in a dome shape. That's the view that we get. I'm not suggesting for 1 minute that that's the real case, but I'm saying that's how it appears, and that's the view that we'll find very useful in mapping the sky. In fact, if you've been to a planetarium, you'll notice that the sky is actually projected onto the inside of a dome, and that gives a very realistic representation of the sky. An observer anywhere on the Earth will only be able to see half of the sky at one time, half of this celestial sphere. So let's look at how we map this imaginary sphere then. In the same way that we defined lines of latitude and longitude on the Earth, we define some corresponding grid pattern on this celestial sphere. And lines that we draw parallel to our terrestrial latitude lines, we call lines of declination. And they run in a very similar way. We have, the same way we have an equator on the Earth, we have a celestial equator corresponding to the 0 latitude line on the celestial sphere. In the same way that we have a north pole and a south pole on the Earth, we have a north and south celestial pole. So let's continue to define that grid system. These are the declination lines. And lines of declination, as we've said, are analogous to the lines of latitude that we have on the Earth. And they're measured in exactly the same units. They're measured in degrees north or south. Okay? So that's pretty straightforward. The lines on the celestial sphere that go the other way, we call lines of right ascension, or sometimes abbreviated to RA. Lines of right ascension then are analogous to the longitude lines on Earth, but they're not measured in the same unit. Remember that we used on the Earth, the terrestrial mapping, we used the degrees east or west of Greenwich because we had a reference point on the surface of the Earth which we could measure things relative to. But when it comes to mapping lines of right ascension on the celestial sphere, remember this imaginary sphere is rotating around us all the time. So no fixed line is over Greenwich. We can't use Greenwich as a meridian. We can't use any particular place on the Earth as a reference and say, well, it's the line above that that's going to be our 0 line reference for right ascension, because the whole thing's rotating around us. So right ascension is measured in hours, minutes and seconds with a range of 24 hours. We'll look at that in a little while. Here's our combination then of right ascension lines and declination lines. The 0 point of declination, we've said, is easier to define. It's the celestial equator. But what about the 0 line for right ascension? It's a little more tricky to define. Now, anyone would like to suggest how we do that? Anyone that doesn't know how we do it, and have any ideas as how we might map, how we might define the 0 point of right ascension? So that either means you all know already, or it means you don't know what I'm talking about. Does anybody that does know want to tell me how we define the line of 0 right ascension?
First point of Aries.
That's right, it's the first point of Aries. Now what does that mean, Bob?
The vernal equinox.
That's right. Remember we spoke earlier about something called the ecliptic. Let me just move that out of the way to become more apparent what that is later. Down there. Yeah, remember we had this this concept of something called the ecliptic, and we said that that's the plane of the Earth's orbit through space. Well, there's another definition of the ecliptic, which is the projection of that plane onto the celestial sphere. Now, because the Earth's axis is inclined at 23.5 degrees to the plane of the ecliptic, so the ecliptic is inclined at 23.5 degrees to our celestial equator. I knew I should have got a wireless mouse. You're right, Jen. Everyone follow that? Good. Okay. So this term ecliptic, then, we've said it can either mean the plane of the Earth's orbit through space, or we also use the term to mean a projection onto the celestial sphere of that plane. And as Bob just mentioned a moment ago, we use that actually to define. Sorry, did I hear a question?
It's not actually in Aries, is it?
That's right. We'll come on to that. Yeah. We'll come on to that in a moment. Good point, Bob. Thanks for reminding me about that. Yeah.
Astrologers.
Yeah, that's right. They probably don't appreciate that. So in our view of the stationary Earth and a rotating celestial sphere, the Sun appears to move around the celestial sphere from west to east once per year along a path inclined at 23.5 degrees to the celestial equator. There's a lot of mathematical sounding words in that, but all it means is the Sun appears to trace out a path through space which is at 23.5 degrees to the celestial equator. And as you'll see from that diagram there, it appears to cross the celestial equator at 2 points. It appears to cross once when it's travelling, so the Sun is moving this way, so it appears to cross once moving north to south in autumn, and it appears once, it crosses once travelling south to north in the spring. And that's what we call the vernal equinox, or the spring equinox in the northern hemisphere. As Bob said, it's called the first point of Aries because, in actual fact, when the constellations were drawn up, that point was in Aries, but it shifts. So what we call the first point of Aries is now actually in Pisces, I believe. Is that right?
Mm.
Yeah. But all it means is the point where the ecliptic, the path of the Sun, appears to cross the celestial equator. That's what gives us our 0 reference to right ascension. Here's just a recap of our grid system. Oh, we have a question. Fantastic.
I have a question, probably a stupid one.
No, go ahead, please. That's what it is.
Although the maths will be different, surely you could have had the line that projects out from the Greenwich line.
Yeah, but the thing is, you see, that the line that projects from the Greenwich line, the Earth is rotating all the time. So the line of right ascension that projects out from Greenwich line at one moment in time will be different a few seconds later, because the Earth is rotating, or in our view of things, the celestial sphere is rotating in the opposite direction. So it's a different line that's over Greenwich all the time.
Yeah, but I mean, you could have done it with maths. You could have done it that way. You could say, well, I know where the Greenwich line is, I know what time it is, I know which way I'm pointing.
Mm-hmm.
Azimuth Mount, isn't it?
Pardon me?
That's what you have to follow that with.
We'll talk about Azimuth Mounts in a little while. I'm not quite sure. I'll talk to you about that afterwards.
Yeah.
I'm not quite sure I'm following how we would get that, because the whole thing, you see the thing about the lines of declination is that a line of declination on the celestial sphere is always above the same line of latitude on the Earth. But that's not the case with the lines of right ascension and longitude. So here we have our celestial sphere again. As you see, we have the lines of declination moving north and south. We have the lines of right ascension moving from 0 through 24-hour range again. And we define our 0 point where the ecliptic, that's this red line, is crossing the celestial equator. So, as we've said, most objects that we map in the sky, stars, nebulas and galaxies, the things that you see in fixed star maps, remain in a pretty much constant position throughout a human lifetime, and so we map those on star maps. We don't map planets on star maps because their positions are constantly changing in a complex way. But if you buy a fixed star map, one thing that you will see that changes its position is, as we've said, the sun, because it changes in a predictable way throughout the year. Its right ascension and declination change throughout the year. And here's a little graphic which shows that. So this is showing how the position of the sun appears to move throughout the year. So here we are in March, the equinox, and then throughout our summer, the declination of the sun climbs, and its right ascension is moving as well, you can see. So coming down to autumn here, we have a declination of 0 again, another equinox, but a right ascension of 12 hours. Going down to our autumn, going down to our winter there, and back up again. So that's just as we see the position of the right ascension and declination of the sun changing throughout the year. And as we said earlier, as we saw in that graphic earlier, the best time to view a particular constellation is when the sun is in the opposite direction. Okay. Here's another little graphic which shows how, in the same way that we saw any point on the Earth can be defined by two coordinates, a latitude and a longitude, so any point on the celestial sphere can be defined by two coordinates, a right ascension line and a declination line. And we can change this little graphic to change the right ascension or the declination. We can show on here the north and south poles of the Earth, the equator of the Earth, the north and south celestial poles, the celestial equator, the 0 hours right ascension circle. And as we say, this graphic's a little bit strange actually, because it does actually show the Earth rotating with that, but this is a bit confusing because it seems to imply that the line of 0 right ascension is always over Greenwich, but of course it's not. It's spinning around.
You're just having to go at me now, aren't you?
It don't work like that.
It doesn't work like that, so it's graphic doesn't show that. And then we can show the ecliptic on there as well, which is, as we've said, inclined at 23.5 degrees to the celestial equator. So that's a summary of the coordinates that we use. Celestial globes then. What's a celestial globe? In the same way that we can have globes of the Earth, you can have globes of the sky as well. If you look at a star map printed in a book, obviously it's in a flat piece of paper, so it's going to distort. If you show a big area, it's going to distort the view. The real way to show the positions of the stars without distortion is to show them on a globe, but of course we'd have to be on the inside of that globe to show it properly. So what they do is they show a globe as if you're on the outside of it looking in. Of course you could never be on the outside of this imaginary sphere, but some globes like this one show the Earth inside the rotating celestial sphere, and some don't show the Earth at all, because you don't really need to, you just need to show what's over it. Now there's a bit of variation in the kind of celestial sphere you'll see. Some of them actually show the constellation patterns reversed, as if you were looking from the outside, to make it, I guess, more realistic to this concept of a celestial sphere. But that makes it very difficult to read the constellations. So some of them, which I tend to prefer, do show constellations the right way round. So you've got to kind of imagine that if you're looking at a particular point on the globe, the rest of the sky is wrapped around behind you as opposed to in front of you. Make sense? It's a lot of baffled faces, getting worried. Either that or I'm thinking something very basic. So as we've said, some of them show the constellations the right way around, which I tend to prefer. Here's a very nice one that I thought I saw a picture of in Sky and Telescope. And some celestial globes have very over-stylized constellation artwork and aren't very easy to read in terms of the constellations. But this one I thought was really clear because it's more like the kind of star map that you'd expect to find in a book. It just shows what you want to know. It shows the constellations, the right ascension and declination lines, the stars and the nebulas and the Milky Way it shows down there. And a close-up of that, you can see it's a really nice star map. It also shows the ecliptic and the position of the sun and the date in certain places. In star maps and on star globes like this, the brightness of the stars is reflected by the size of the circle drawn to represent them. Obviously some stars that we see are brighter than others, but they all appear the same size to the human eye. So we represent that on star charts, on star maps and star globes, by showing a brighter star as a bigger dot. So those two stars, the brightest stars in the constellation of Gemini, are brighter than that one because they're represented bigger and much brighter than these ones here. So, how much of the sky do we actually see from a particular point on Earth? Here is an image of the Earth, not a real image, but a computer graphic image, seen from over the North Pole. Now, if we were to stand at a point over the North Pole, and we'd see the Earth rotating, we would always see only one half of the surface of the Earth at a given time. But the thing about it, if we stood over that point on the North Pole, we'd always see exactly the same half of the Earth's surface, day in, day out, throughout the whole year. We'd never see anything except that particular 50% of the Earth's surface. We never see anything south of the celestial equator from that vantage point. We see the North Polar region clearest because it's in the centre of our field of view, and we see the equatorial regions less clearly because they're distorted by the curvature of the Earth. Now, in a similar way, if we were to stand on the Earth and look up at the sky, again we'd see one half of the celestial sphere. This is an image taken from popular program Stellarium that I'm sure a lot of us use. And if we were to stand on a point on at the North Pole, we'd have a very similar situation. We'd see the sky rotate around us, but again we'd see only half of the sky at any one time, and we'd always see exactly the same half of the sky at one time. As the Earth rotated, we would always see exactly the same stars. We'd never see anything south of the celestial equator, and we see the North Celestial Polar region clearest because it's overhead, and it's coming the light from things which are overhead is coming through less atmosphere, so they're clearer to see. We'd see the equatorial regions less clearly because they're coming through a lot more atmosphere, and things on the horizon or close to the horizon are always less easy to see on a planet with atmosphere than things which are overhead, for precisely that reason. What about if we had a vantage point over the equator? In that case, again, we'd only see one half of the Earth's surface at any given time. But the difference now, of course, is because the Earth is rotating, we're over the equator, although we only see a half of it at one time, we would see a different half of the Earth's surface as it rotates. During the course of the day, we'd see the entire surface. But the limitation of that is we see the regions on the celestial equator clearest, and in this case we see the polar regions less clearly. A completely analogous situation occurs when we're looking at the sky. Again, we only see one half of the celestial sphere at a given time. But this time, as the Earth rotates, we see a different half of the celestial sphere. So, from a point of view on the equator, we can see all of the sky, theoretically, at some point or another. During the course of the day, I said we see the entire sky. But why not? Well, in actual fact, we don't see the entire sky during the course of the day because at some point during the day it's daylight and you don't see the sky at that point. So we're going to have to wait until 6 months later when the Earth's the opposite side of the sun to see equatorial regions which are high in the sky when the sun is. Okay. And we see the polar regions this time less clearly because they'll always be on the horizon. Here's a little graphic showing how the observer's latitude is going to affect what we see in the sky. Let's set it to something like, what's our latitude? We said about 3 degrees, something like that. So from our kind of latitudes, you'll notice actually that you can divide up the stars that we see into 3 categories. You've got these which are represented by the orange region here, are what we call circumpolar constellations. So from the point of view of an observer at that latitude, all of the objects in the sky which are in that orange range will never set. They'll always appear to be in the sky. So you'll see them at the night time, at any time of the year. Anything in the blue region are rise and set stars, which means that during the course of the day they'll appear to rise and they'll appear to set. If the stars which are in that range of declinations are in the sky in the daytime, then we won't see them at that time of year. We'll have to wait until 6 months later to see them. So we've got the circumpolar stars that we'll see at any time of year, and the rise and set stars, which we'll only see at given times of year, depending on whether they're rising when the sun's in the sky, or whether they're rising at times when the sun's set. And then the third category is what we call never rise stars, stars which are too far south on the celestial equator to ever see. Remember that we said that if we were standing at the North Pole, everything between 0 degrees and 90 degrees declination would be circumpolar. We'd always see it. Oops, I've got the wrong way around, it's flipped upside down. There it is. We suddenly went from the South Pole to the North Pole to the South Pole with the blinking of an eye, which was quite impressive. So there's our circumpolar region for an observer at the North Celestial Pole. Everything is circumpolar. Nothing ever rises, nothing ever sets. And there's a whole 360 degrees, 180 degrees of the celestial sphere which an observer there would never be able to see. Likewise, if we pull him down to the equator, observer at the equator, everything rises and sets. There's nothing he can never see, and there's nothing that's circumpolar. There's nothing that he can see all times of the year. Everything rises and sets at some point of the day. But from most latitudes, including ours, we're going to see a range of stars that rise and set that we can only see at certain times of year, and a range of stars which are circumpolar that we can see any time of year. Here's a little graphic that shows the position of the moon's orbit in relation to our celestial sphere. The moon's orbit, the plane of the moon's orbit, is actually inclined at about 5 degrees relative to the ecliptic, which means it's inclined at about 5 degrees plus 23.5 degrees, almost 29 degrees, more than 29 degrees, to the celestial equator. So it's not exactly on the same plane. It's inclined an additional 5 degrees, so it's nearly 29 degrees relative to the celestial equator. And the points where the moon's orbital plane crosses the ecliptic are called the nodes of the moon's orbit. An ascending node is when the moon is moving south to north across the ecliptic, and a descending node when it's moving north to south. And the existence of these nodes tells us why solar eclipses only occur when the moon is new and it's at one of the nodes of its orbit at the same time. So that explains why, unfortunately, we don't see a solar eclipse every month. This is getting in the way. There's another little graphic showing these points we just mentioned, the nodes of the moon's orbit. And you can see it's only when the moon is at those points, or very close to them, that its direction in the sky will be the same as the direction of the sun. And we can possibly get a solar eclipse. Let's talk a little bit about the apparent motion of the objects in the sky. And we've said things rise and set, but let's think about the sun, how it rises and sets. From the point of view of this analogy, I'd like you to imagine that you're looking towards this screen here, and this direction is south. Okay? So I'm south of all the people there. The back towards the kitchen is north. That wall is your east, and this array of windows is your west. Okay? Now, on a flat screen here, I've had to show that all squeezed into a single view. So really, east is over there and west is over here. But we're just imagining this whole view is squeezed in. So on the March equinox, which we said is the time when the days and nights are of equal length, the sun will rise due east in the sky. Throughout the course of the day, it will move, it will rise in a direction up and to the right, and describe an arc across the sky, reaching its highest point in the sky at noon, at which point it will be due south. Throughout the day it will then continue, and it will set on this date due west. So an arc from due east exactly to your left to due west exactly to your right on the March equinox. What about in June, the June solstice? June solstice, which is the longest day of the year from the northern hemisphere, the sun is going to rise much further north than east, so it's going to kind of rise somewhere towards the door where you came in from your point of view. It's going to move across the sky, it's going to get higher in the summer solstice, and it's going to still reach its highest point at noon. When it sets, it's going to set further north than west, so somewhere towards that back window. Moving on to autumn, our September equinox, around about September 21st, we've got the same kind of situation as we had in spring. The sun again is going to rise due east. It's going to be at its highest point at noon, due south, and it's going to be at it's going to set at the point due west. And then in December, as you probably predict, it's going to rise further south than east. It's going to climb in the sky to a much lower position, and it's going to set somewhere south of west. And a little bit later on, we'll look at this diagram again, but we'll look at it with these imaginary lines of right ascension and declination superimposed on the sky. So we'll see a lot easier why that happens to be the case. But here's a summary from the point of view of an observer in the northern hemisphere. The objects appear to move across the sky in an arc. On March 21st and September 21st, the two equinoxes, they'll appear to follow this path, which is the path of the celestial equator actually. In December, they'll appear to follow a lower path across the sky. And in summer, they'll appear to follow a higher path across the sky. Here's another diagram showing what we spoke about a little bit ago, which is that we have some stars which appear to never set, the circumpolar constellations, some stars which appear to rise and set, and some stars in this pink region which appear to never rise from a particular latitude. So, from our point of view in the northern hemisphere, if we look south, objects including the sun and the stars as well appear to move across the sky from left to right. So they rise moving upward and to the right, and they set moving downward and to the right. Looking north, objects appear to rotate around the north celestial pole in a counterclockwise direction. If you were to look north behind you, they'd appear to be going the opposite way to the clock around the sky. In the southern hemisphere, of course, everything's going to be reversed. In the southern hemisphere, if you look south, everything will appear to rotate around the south celestial pole, but in a clockwise direction. And if you look at an object rising and setting, things will still appear to rise in the east and set in the west, but this time you'll be looking north, and you'll see things move from your right across the sky and down to the left. It is a little bit disorientating actually to see the sun go the wrong way across the sky. At least it is for those people that actually pay attention to those things. Oh, look, the sun's going all the way across the sky. Here's just another definition that I'd like to mention, which is something called the observer's meridian. I think this is probably the last term I'll introduce. And all the observer's meridian means is an imaginary line drawn across the sky from north to south. Why is that important? Well, as we've said, that when an object is due south, it's at its highest point in the sky. So from the point of view of astronomers who like to look at things in the sky, when an object is highest, it's quite important. So we talk about when an object's crossing the meridian, crossing the observer's meridian. All it means is when it's crossing his north-south line. So that's simply a line drawn from north to south. That's an important concept because an object will be at its greatest elevation when it crosses the meridian. Any questions, anybody?
Me?
Yes.
When does winter start?
Pardon me?
When does winter start?
When does winter start? Well, the December solstice, I never was sure whether that defined the middle of winter or the start of winter. I think it's defined by the winter solstice, am I right?
21st of December.
Yeah. Yeah, I think we define it as the solstice, which is the point when the axis is most pointed away from the sun. Feels like it started already, actually. So, as we've said, just as the sun is at its highest point in the sky when it's due south and crossing the meridian, so all other objects that we might want to look at are also at their highest point in the sky and best placed for observation when they're crossing the meridian. Here's a little graphic which shows this imaginary celestial sphere and an observer at different locations and what his point of view would look like. So if we move him, if we move the latitude of our observer to somewhere near the pole, we can see that what he sees is a view of the sky with the north celestial pole directly over the top of it, and lines of right ascension going directly radiating out from that. That's nice, that, isn't it? I like it. If we move our observer's latitude to somewhere on the equator, or thereabouts, what he will see of the celestial sphere is the two celestial poles on his horizon in a north and south direction. You get the idea of that. Here's a kind of parallel view showing the how the celestial sphere, how the Earth really rotates. Let's just so that view to the left is showing how the Earth is really rotating, and how an observer on Earth sees the celestial sphere appear to rotate around him. So when you're out looking at the sky, I'd like you to imagine that you've got this grid line over your head, and it's going to be a really useful way of helping you find your way around the sky. Although we know what's really happening is that everything in the sky is fixed. We can put actually add star randomly. What's that? Look. We can randomly add stars to our imaginary celestial sphere, and they're pretty much in the same direction as the Earth rotates, but from the point of view of the observer on the Earth, you see as he's looking south, they appear to, just like the sun, they appear to rotate around him from left to right. And as we change our location, let's put it somewhere here, as we go further towards the pole, the position of the celestial pole in the sky appears to be higher up, and we can see fewer southern constellations. Here's Anthony up in Iceland. We can see that he sees a lot more constellations circumpolar, that is never rising or setting, but a lot less of the southern stars.
Not seeing much aurora.
Pardon me?
Not seeing much aurora.
No, I know, it's a poor animation, isn't it, really? So this region here shows the stars that never rise or set. That shows the stars that do rise and set. And as you see, as we change the latitude, so that's the animation rate, good right now. As we come down in latitude, there's a bigger region of stars that rise and set, and a smaller region that are circumpolar. Okay.
So really, if you want to be an astronomer and see all the sky, you've got to be on the equator.
I guess ideally, or spend part of your time at the northern latitude and part of your time at the southern latitude.
Better move.
That's in theory anyway. Not sure what that one shows. It's just another very similar animation. This one shows the path of the sun across the sky, and the path during the course of a day, and the path of the sun across the sky during the course of a year. So during one day, the sun, as we've said, appears to follow an arc across the sky like this, but during the course of the year, it will appear to follow this red line, which is the ecliptic. So that's just showing the year going. But this is showing noon at the same time of day, noon, at different dates during the year. So you can see what's actually happening is that the sun is following that yellow path across the sky during one day, but during a year it's following that red path. It's moving a little bit on that red path every day. Again, as we change latitude, somewhere near the equator it's going to be much higher, and as we go towards the pole it's going to be much lower. What this one shows actually.
That's very similar.
It's very similar, isn't it? Okay. So yeah. So the difference with this one is that
It even goes faster when you get older.
I've not noticed that yet. I'll stop it now. I knew there'd be a technical. Oh, there you go. There's the mouth. The thing about this one is that that one we saw before, it only allowed you to show the position of the sun at noon, how it varied throughout the year. But this allows us to vary the time of day or the time of year. So as we change the time of day, you see, we can move the animation. So at a particular time of day, on a particular day, we can move the time and see how the sun moves across the sky. Or at a particular time of day, we can see how it will be at a different position.
You get to October.
Yeah. Let's put it to October, late October. So we're here, and what's that blue line? So there's the night time, the sunset, and when it rises, it's going to follow that path. Oh, I think the blue line is the celestial equator. Another coordinate system, which Bob mentioned a little while ago, was altitude and azimuth. We define points in the sky as having a declination and a right ascension, but from the point of view of an observer, we want to know how high they are in the sky and in what direction. So we have this other coordinate system that we sometimes use called an alt-azimuth, altitude and azimuth coordinate system, where we just define the azimuth, which is the direction from north, and the altitude, which is how high. So if you wanted to know where a particular object was, yes, you would get it from star maps by a right ascension and declination coordinate, but in terms of where to look on a particular night, you don't know, okay, so that's great, it's right ascension and declination are these values, but which direction do I look, and how high do I point the telescope? So that's where altitude and azimuth come in really useful. So said, altitude or elevation tells us how high to look in the sky, and azimuth tells us what direction. That's another little graphic which just shows how altitude and azimuth.
So really, you've got to know. You've got to know the position from north. That's where your datum line is.
Yeah.
From north, the actual north meridian, as it were, round to where the actual star is.
That's right. Yeah.
On its altitude line.
Yeah.
So you've got to, if you're trying to compare your maps in your book with the actual sky, you've got to know the difference between the position of your star from the north before you start attempting to assess its altitude. What I'm saying, it's moving all the time.
That's right.
If you look in your stellarium and you look at the position Azimuth, they're both flickering like mad because it's changing all the time.
It is moving all the time.
That makes it a bit complicated.
Yeah.
It's all right when you're going to go to scope. That's Azimuth.
That's why in fact you've got advantages of both coordinate systems. The right ascension and declination coordinate system. A particular object is at a particular location. It never changes. But the disadvantage is that it doesn't immediately tell you which direction to look and how high to look. So the advantage of the alt-azimuth coordinate system is it tells you which direction to look and how high to look. But that how high to look and which direction is constantly changing. At a particular time, yeah. So it only works at a particular time.
Second or minute.
Yeah. Which is why we'll.
I'm soon not the Equatorial any day.
Yeah. Well, I mean, this is not just for scopes. This is just a coordinate system. You might, if you're out without a scope, and you know the right ascension and declination coordinates of a particular object, and you just got a pair of binoculars, you might have a compass with you to say, okay, that's north, so I'm going to be that kind of direction and that kind of height in the sky. So it's useful when you're just out observing with a pair of binoculars or with the eyes as well. Here's a little conversion thing that I found online, which allows you to put in declination and right ascension coordinates. And as we were saying, you have to put your declination coordinates in and your right ascension coordinates, your latitude and longitude, and the date and time of year, and then that'll give you the altitude and azimuth, and that's changing all the time. So that's just a freeze frame screenshot of a little converter that I found at that location.
Is your latitude and longitude where you are at the time?
Yeah. Yes, the observer's latitude and longitude. So
You've got to know that regardless, haven't you?
Yeah.
You've got to know the latitude and longitude, otherwise you basically can't find anything.
Because as we've seen in those earlier graphics, as your latitude and longitude changes, so a particular object in the sky will appear at a different elevation.
But as far as azimuth goes, you're going from the equator, aren't you? From the celestial equator to the north.
No, you're going from your horizon.
No, sorry, you're going to the horizon.
Yeah.
From the horizon.
But your horizon is moving depending on your latitude and which direction you're looking.
Yeah, I've never liked it.
That's probably why we prefer Equatorial Mount. Certainly in the days before computerized controls. Let's have a look at circumpolar constellations. We've said that some constellations never rise and never set. Just imagine that that line there represents the ecliptic. That's the plane of the Earth's orbit through space. And here's the Earth in March. Why have I not drawn it tilted? Because in March the Earth is moving within the direction of its tilt. So in actual fact, which way round will it be? The axis of the Earth in that view, you've got to imagine that it's tilted away from you. Okay? So that's March. So here's a question for you guys, because you're not asking me questions, so I'm going to ask you a question. Which direction, in terms of right ascension, is that, over that way? Any offers? You've got 1 in 24 chance of being right. Bob's going to give me an answer.
To the left.
To the left is what? Which direction?
Going anti-clockwise. No, going clockwise.
We're looking at the plane of the
But
ecliptic.
still
so-
the same, ecliptic.
Yeah.
March. Oh. Yeah, it's got to.
What?
If it's right, just you're talking about right ascension.
Yeah.
It's got to go. I'm not quite following you.
Now the question I'm asking is,
Yeah.
if I said, what direction is that toward that wall? Is that 5 hours right ascension, 24 hours right ascension, 3 hours right ascension?
12. 12.
How about 12?
12.
Alfred?
No.
What did you say, Dave? 12?
No.
Any other options?
6 hours.
6 hours.
6 hours right.
We've got 2 6s and 2 12s. Any other offers? 12 hours right ascension, have it. Why is that? Remember
This way now.
Remember how we defined the 0 hours of right ascension? It's the direction of the sun on the March equinox. So on the March equinox, the sun is at 0 hours right ascension over here. Okay?
Going.
Yeah.
So the opposite direction would have to be 12
12
hours
hours, yeah.
right ascension. 12 hours out.
Of course it
Here's the sun. Here's the Earth 6 months later in September. So obviously this direction is 0 hours. So March is going to be a very good time of year to view constellations, rise set constellations, which are in the 12 hours direction, actually anywhere between maybe 6 hours and 18 hours. But anything that's at 0 hours right ascension, not a good time to view them in March because the sun's in that direction. And in September, of course, the opposite's true. Good time to view things that are in the 0 hours direction, but not a good time to view things in the 12 hours direction. Follow?
is. Yeah.
Good. Here's a familiar constellation of the Plow, and the X is representing the North Celestial Pole. Now it's difficult to represent this really on a flat screen, but I want you to imagine really that the Plow is kind of over the plane of the observer. So I've got an observer here at some mid-northern latitude, an observer here at some mid-northern latitude 6 months later. So, from the point of view of this observer, if he looks at the position of the Plow relative to the North Celestial Pole, you can see that when he's looking at the North Celestial Pole, he's looking a bit lower than he has to look to see the Plow. So that time of year, at night time, he's going to see the Plow pointing downwards to the North Celestial Pole. From the point of view of our observer here, when he looks into the sky, when he sees the North Celestial Pole, he's looking a bit higher than when he sees the Plow itself. So from his point of view in September, he's going to see the Plow pointing upward to the North Celestial Pole. So although we see the Plow throughout the year as circumpolar, when it's night time, in March, we see it upside down, as it were. When it's in the sky and it's the right way up, it's daytime, so we don't see it. In September, at night time, we see it the right way up, but when it's in the sky in daytime, it'll be upside down. So in spring, the Big Dipper or the Plow points downward toward the North Celestial Pole, whereas in autumn, it points upward to the North Celestial Pole. So if you don't know what time of year it is, you're on a desert island, you think, what time of year is it? Well, you know you're in the Northern Hemisphere if you can see the Plow. If you don't know what time of year it is, have a look at which way up the Plow appears to
The
be.
equator there.
Pardon?
It comes to be the equator.
It's going to be
See,
equator,
you can't see it,
it's going to be
you
really,
can't see it.
it's going to be really nice, yeah. Yeah. Here's a little animation which shows that how through the course of the year. So this allows us to change the time of day or the time of year. So let's imagine the same time of year, the same time of night. Let's imagine 12 a.m. and March. And we've said in March it's pointing more or less downward. So as we go through the year, in June, at midnight in June, it's going to be kind of pointing to the right toward the pole star. As we go towards September, as we said earlier, for the reason we saw it in that graphic, you're going to see at midnight the Plow pointing upward toward the North Pole star, towards the North Celestial Pole. And as we go into December, as you'd probably expect, you're going to see it pointing kind of to the left. So that's the variation that we see at the same time of night throughout the year. Let's have a look how the time of day changes for a particular time of year. Let's move this hand here. So you can move the position of the Plow relative to the. You see, when it's pointing upward in March, it's daytime, so we wouldn't see it. We've set animation to the system clock, which is now, which is 20 something. You probably see something like this. Okay. So we follow why we see the circumpolar constellations at different orientations in the sky at different times of year. What about equatorial constellations then? How does our view of equatorial constellations change? Well, as we said earlier, to see equatorial constellations, you've got to be at the right point in the Earth's orbit, because there's going to be a time of year when they're high in the sky at the same time that the Sun is. So at that time of year, you won't see them. Let's imagine the ecliptic again. The Earth, axial tilt, and the Sun in that direction. So that's the nighttime side of the Earth. So this is the this is the northern winter, because the north pole of the Sun is pointing away from the Sun. Our night times are longer and our daytimes are shorter. So another question: what direction of right ascension is that this time?
Zero.
We have a 0.
12.
We have a 0 and a 12. Maybe you did well last time. Do you want to take a guess or a calculation?
Is it 18?
We have a 0, 12 and an 18. A good spread there. One of you is going to be close.
6.
Actually, I don't know if you were close. That would be a good quiz question, wouldn't it? Why is it 6 hours? Because this is the northern winter. And in the northern winter, the Sun in the sky is at 18 hours of the December solstice. So the opposite direction there is 6 hours. And a familiar constellation in the direction of 5 or 6 hours of right ascension, excuse my little stylized representation of Orion there. Why have I drawn it down there and not here? Because that's the ecliptic, not the celestial equator. Okay? Celestial equator is at right angles to the pole. So that's a constellation which is somewhat actually very far in that direction, but I've had to draw it within the slide, so just kind of imagine it's a long way in that direction. So here's an observer at some mid-northern latitude, and here's his friend at some similar kind of latitude in the southern hemisphere. Our northern observer looks towards Orion and sees the familiar shape. But I think you can see very clearly from the point of view of our southern observer, looking at the same stars in the sky, is going to see the pattern inverted. Okay. So in the northern hemisphere, where we are, Orion we recognise as a winter constellation. It's high in the sky, looking south, see it's looking towards the south, in winter. But in the southern hemisphere, Orion is high in the sky, looking north in the summer, and it's upside down. And it's very disorientating to see Orion in the northern sky, in the summer, upside down. Here's a photograph taken back in February from the North Island of New Zealand, and February, of course, in New Zealand is late summer, so Orion at this time, I think it was about 10:30 at night, is setting, so you can still see it a few hours after sunset, but it is setting, and of course it's setting in a right to left direction, so it's moving across the sky. It's rising over there, it's rising to the left, it's moving across the sky, and it's highest in the sky in the north at midnight, and then it's going downward, setting towards the western horizon, which is to the left. It's setting in the direction of the arrow. So of course you follow the stars of the stars of the belt upward to Sirius. You look for the Orion nebula above the belt.
Yeah.
And try to get, if you ever encounter anyone that believes the Earth's flat, ask them to explain that. I don't think they will. Here's a question then. What is a day? We're going to come on to this concept of sidereal time now. Anyone like to give me a definition of what they would use as to define a day? What is a day?
Well, it's the time the Earth takes to rotate on its axis.
Okay. Good definition. I'll go with that. Any other definitions? Jed, are you still awake? Liam?
Yeah, he's quiet.
What's a day? If I said to you, what's a day?
24 hours, 56 minutes.
How many?
That's the solstice. The
Yeah.
solar day is 23 hours, 56. No, shorter.
Which is shorter? We'll go on to this in a minute.
Yeah.
We'll understand why. Is everyone okay, by the way? It's got, dropping off yet.
Think about it.
The time taken for the Earth to rotate once was the definition given by Brian. It's a good definition. It's one of the ones I have up here. Any other definitions of what we might call a day? Maybe we could say it's the time taken for the Sun to cross the meridian twice. So it rises, it reaches its highest point in noon, it crosses the meridian at noon. Time taken for it to do that once, before it does it again. Maybe we could call that a day. Or maybe we could just say, well, it's 24 hours. In actual fact, these are definitions of different things. These definitions here, the time taken for the Sun to cross the meridian twice, or 24 hours, are the definition of what we call a solar day. However, time taken for the Earth to rotate once on its axis is something a little bit different. It's what we call a sidereal day. And as Bob mentioned, it's a little bit different. It's a little bit shorter. In fact, it's quite a bit shorter. It's 23 hours and 56 minutes. It's probably more accurate than that. You could say it's so many seconds. Yeah. In round numbers, to the nearest minute, is 23 hours and 56 minutes. The time taken for the Earth to rotate once on its axis is actually a significant amount less than what we traditionally call a day. Your wristwatch is going to measure a day as 24 hours, but the Earth spins a little bit faster than that. So let's have a look at why these are different. Why is what we traditionally call a day different to the time taken for the Earth to rotate once on its axis? Here's the Sun and the Earth, again, not to scale. And I don't know if you can see that little red line put on there. You see that at the back? So that represents the longitude line of an observer. So we're looking down on the plane of the ecliptic at the Earth rotating around the Sun. And we're going to imagine an observer at this point here. Okay? He's looking in this direction. He sees the Sun, and I want you to imagine that he sees some distant star way over in the same direction in the sky. So from our observer on the Earth, and we'll imagine that it's in the northern hemisphere, so he sees the Sun looking south, and what he's going to see is the Sun and some distant star in the same direction, both due south, as he's at that point as the Earth rotates. Now, if the Earth just rotated on its axis and stayed in the same position relative to all the background stars, you'd see the same thing day after day. But in actual fact, what happens is when the Earth has had time to rotate once on its axis, it's also moved a little bit in its orbit. Okay? So it's spun through 360 degrees. And in addition to spinning 360 degrees, it's also moved a little bit in its orbit. So look at what's happened. The direction of a distant star is now still in the same direction that it was before, because it's very much further away than the Sun. But from the point of view of our observer on the Earth, the Sun is not in the same direction anymore as that distant star. In order for that, for the Sun to be in the same direction, in order the same direction as it was before, it's going to have to rotate a bit more. So what's our observer on the Earth going to see now looking south? It's going to see the distant star again crossing the meridian, crossing the north-south line, because the Earth has rotated once, or from the point of view of the observer, the star has appeared to go across the sky, set in the west, appear to rotate all the way around the Earth, rise in the east again, and get back to the same point in the sky. But what about the Sun? Where's the Sun going to appear to be to our observer? Further,
The west.
one says further to the west, one says further to the east. One of you's going to be right. Okay, so the Earth is rotating west to east, which means it's going that way. Okay, it's not quite gotten back to the point where the Sun's in the same direction in the sky. So remembering that things rise east to west, it's a little bit behind. When the Earth has rotated once, the Sun has not quite reached the same point in the sky. It's slipped slightly to the east from the point of view of a geocentric view. Imagine that we're at the centre of all things. In order for the Sun to cross the meridian again, we've got to wait a little bit longer. You see that? So the Earth is going to have to spin a little bit more in the sky so that that red line is pointing to the Sun. So here we are a little while later with the Earth having rotated that little bit more. So now the Sun is due south again. But now the distant star is not in the same direction. Here's our observer's view on Earth. Here's the Sun, it's now back due south. So where's the star in the sky now? A little bit further west, that's right. Now, that time there is what we call a solar day. That's the day that that's the time that we traditionally measure as a day, because we want to know where the Sun is in the sky in our day-to-day lives. It's what determines whether it's daytime or nighttime. So our traditional 24-hour day is defined as the time taken for the Sun to cross the meridian twice. This time, for a distant star to cross the meridian twice, is a little bit shorter, and that's what we call a sidereal day. Brian's going to ask a question.
No, I'm just saying I'm glad the books don't go side by sidereal time.
Yeah, wouldn't work, would it? Wouldn't work. So there's our 24 solar hours, and these hours here are solar hours as well. But we could just as easily define a sidereal day as 24 hours. We could call it 24 sidereal hours. Now that's not a problem, because in many areas of science and engineering we use different units for measuring the same quantity. We might measure distance in miles or kilometres. We might measure temperature in Fahrenheit or centigrade. You might fill up your car in gallons or litres. So it's not a problem to have different units to measure the same thing. But it's just the same thing with time. Most people think you only measure time in one unit, hours, minutes and seconds. Well, in astronomy we can have two different units, but unfortunately they're called the same thing, hours, minutes and seconds. But we've got solar hours, minutes and seconds, and sidereal hours, minutes and seconds, which are a little bit shorter. Okay? So just think of two different sets of units that we can use to measure time. Here's a gift idea for the astronomer who has everything. Just an interesting little image that I found of a wristwatch showing two clock faces, one keeping
Wall Street, yeah.
one keeping solar time and one keeping sidereal time. It might be a lot easier and probably a lot cheaper to download an application for your mobile phone or something, it's just the same thing. But I thought it was a nice little image. Any questions at that point? I'm getting worried now because it either means that everybody that I'm talking to knows all this already, or it means you haven't understood a word that I said.
So, if you're using the telescope to declination RA,
Yeah.
you point it towards the North Star, you use that as your starting point to find dead objects.
Well, it's actually what we tend to do is we'll come on to that in a little while, but the mounts allow us to set the direction that they're pointing by aligning them to the pole, to the celestial pole. So what we tend to do is if we know the declination and right ascension of an object, we need to know the sidereal time. That tells us where to set the right ascension dial on the setting circle. And I'd like to come on to that a little bit later, if I may. And just put that to the side for now. I don't want to answer your question, but I want to just probably introduce a few more ideas before we go on to that. Okay. Any more questions? I'll ask some questions. How many days are there in a year? 365 and a quarter. Okay. Go with that. Here's another question. The clue is it's not the same answer. How many times does the Earth rotate on its axis in a year? Six. Remember that the time taken for the Earth to rotate on its axis is what we call a sidereal day. But these days we're talking about here are solar days. And a sidereal day is a little bit shorter. So the sidereal day is...
So that's why you get leap year, which is 366 days. That's allows you.
Actually, it's not. I don't think that's the reason that's not the reason we get a leap year, because the number of times the Earth rotates on its axis every year is 366 or 366 and a quarter. But that's every year. You get 366 and a quarter sidereal days every year, because what we call a day is a little bit longer than a sidereal day. The sidereal day is a little bit shorter, so there's going to be more of them in a year. And in every sidereal day, the Earth moves 1/365th and a quarter of its distance around the Sun. So it's got to rotate that little bit more for the Sun to get overhead. So in one full year, it's done one full rotation more. Make sense? Good. So they're solar days, sidereal days. So Liam, if anybody asks you at school, how many days are there in a year, you want to sound really clever, say, well, is that solar days or sidereal days? Because there's a difference. They'll probably kick you.
There's a different way of looking at it as well, Neil.
Okay.
They're going to change anyway, because the Earth's slowing, its rotation rate over time. Because the moon's acting like a brake,
That's right, actually, yeah.
so that will increase. We're talking billions of years, but that will increase over time. So if Liam really wants to be clever, you should say, how fast is the Earth spinning?
Yes. That's true as well. Slowing down, we'll be slowing down, won't it? Yeah. Yeah, it's slowing down. Yeah.
Because the moon's effectively a brake. As the moon goes out,
Yeah.
because it's receding, it's following the south like a brake.
So in the remote past, then, there would have been more days in a year.
Yep.
Because it's spinning faster, so there would have been more days in a year.
Yeah. Yeah.
Yeah, actually, I've heard that on little videos I've got. That's right. So in 1 year, the Sun rises and sets 365 times. But in 1 year, the stars, or the constellations, rise and set 366 times. Okay. What about time of year and how that affects what we see? We're still okay for carry on?
No, I need to leave, I'm afraid.
Pardon?
I've got to be working half an hour.
Oh, okay. Thanks ever so much for that.
Cheers, thank you very much.
Appreciate it. Okay.
What time do you want to have a break?
Uh,
Depends how much.
Sidereal.
Or lunar
Well, I'm just thinking it's 9 o'clock, isn't it now? So
Do we normally break at 9 o'clock?
yeah, around about 9. Yeah. So if you want to, have you got a natural point where?
That's probably a good point, isn't
Yeah.
it?
Okay. Well, if we have a break now, then we'll come back in 20 minutes, half an hour, and then. Yeah. Is that okay with everyone?
Sidereal.
Oh, no,
You're one of those researchers now, don't you?
Yeah, I do.
He isn't. Come on then.
I've not sent you to sleep yet, have I?
Not what?
I've not sent you to sleep yet.
Chrissy? Yeah. Chris, put the lid on and come and sit down, mate. Yeah, put the lid on.
Are we done then?
Okay, folks, continuing on from where we were, hopefully not introducing any new ideas, but just going back over what we've already discussed. Nice one, Chris.
Again. No switch is there. No switch is there.
No, it's all right.
No, that's fine.
Oh, it's
yeah.
all right. Okay.
Okay, so there's our sun, and here's not quite a perfect circle, but here's our sun and the Earth's orbit through space. Here's the Earth on March 21st, the spring equinox. 3 months later, the Earth has moved. We're looking from the north pole of the sun, so the Earth has moved that way around the sun, and here we are in the summer solstice on June 21st. Here we are on the June solstice. Here we are in the autumn equinox, around about September 21st. And here we are in December, I mean.
It's sidereal time again, you see.
Yes, I'm ahead of myself. On December
Your
21st.
time getting you.
What direction's that? Right ascension wise?
Great.
We have a 6, did we? We have a 6.
See the 6 or the opposite to 6, 18.
Remember how we define the direction of 0 hours right ascension. It's the direction of the sun on March 21st. Okay?
No, that's 12, isn't it?
So on March 21st, the sun is in the direction of 0 hours.
Oh, so it's 0.
So that is 0 hours. Okay? 3 months later, the night side of the Earth is pointing towards the 6 hours. That's why it's a good time to view Orion, which is around about the right ascension of 5 or 6 hours. So go back online. September 21st, an observer in this position here is at midnight, so over his meridian is the line of 0 hours right ascension. 3 months later, we've not lost the connection again.
Flashing on and off.
How bizarre. Okay, if it goes again, we can forget it. 6 hours, 12 hours right ascension, and 18 hours right ascension. So when we talk about time on a 24-hour clock, 0 hours is midnight, 12 hours is noon, 6 hours is 6 in the morning, and 18 hours is 6 o'clock in the afternoon. So when we're talking about solar time, an observer at this point here in September, it's his local midnight, it's 0 hours solar time for him. But look at which hour of right ascension is over his head, 0 hours. So on September 21st, the sidereal time is exactly in sync with solar time. If you looked at your sidereal time and you looked at your watch on September 21st, it would be exactly the same. 3 months later, remember that sidereal time is gaining 4 minutes a day relative to solar time. So So in late December, the line of right ascension that's directly over an observer at midnight, i.e. solar 0 hours, is 6 hours. Okay? So at that time of year, sidereal time is 6 hours ahead of solar time. 3 months after that, continuing the same pattern, sidereal time has continued to gain 4 minutes a day. So at this point, an observer here, it's his solar midnight, so it's 0 hours solar time for him, but crossing his meridian is the line of 12 hours right ascension. So in March, solar time and sidereal time are out of sync by exactly 12 hours. Okay? And then in June, as maybe you predict, sidereal time is, you can either think ahead of solar time by 18 hours or behind solar time by 6 hours. Amounts to the same thing. What about tonight, October 21st, October 20th even? October 20th, the Earth has moved in its orbit about 1/3 of the way between the September equinox and the December solstice. So for an observer at local solar midnight here, what line of right ascension is going to be over his head?
2 hours.
2 hours. Absolutely spot on. So, October 21st, we'd expect sidereal time to be 2 hours ahead of solar time. Here's our sidereal time. Oh look, it's only 1 hour ahead. Why is that?
It's summertime, not wintertime.
It's summertime, because we're on daylight savings time. Well, our clocks are now showing 9:30 or 9:33 in a bit. But our clocks are advanced, we'll put them back again next week. So true solar time is actually about 8:30. So that's what this little gadget is down here. It's a little application you can download. It's just keeping sidereal time. So that's telling us that directly over our heads right now would be the right ascension hour of 22 hours and a half, crossing straight over our north-south meridian. Okay, that's all sidereal time means. It means what line of right ascension is crossing our meridian at that moment. And it's gaining 4 minutes a day relative to solar time. This particular animation always displays that every time. I don't know why. It's no different to the rest of them. So here's another little animation which is showing solar time relative to sidereal time throughout the day. For some reason they show it on the vernal equinox, which is spring, when solar time and sidereal time are exactly 12 hours out of phase. Let's put it in autumn when they're exactly in sync. We said before in our previous slide that in September, solar time and sidereal time are exactly in sync. So this little animation allows us to advance the time by solar days or sidereal days. If we advance by 1 solar day, so that's the time taken for the Earth to rotate once on its axis and rotate that little bit more to bring the Sun back to the same point in the sky, we can see that solar time is back at 12 AM, midnight. But look what's happened to sidereal time, it's a little bit advanced. And we can use this animation to move to different points in the year and see how at any point of the year, at any time of day, we can see the relationship between solar time and sidereal time. We can put our observer at midnight, we can put him at noon, we can put him at sunset or sunrise. We can go forward by sidereal days instead of solar days in any increments. That's a nice little animation that helps to show the relationship between solar time and sidereal time. So here's a little chart that I drew up to show throughout the course of the year where is the Sun, what's the right ascension. Right ascension, you can just think of which direction. Where is the Sun at midnight, mid-month, and which line of right ascension is crossing the meridian at midnight. So in January then, the right ascension of the Sun is in the direction of 8 hours. The sidereal time at midnight is 8 hours, So that means it's going to be a good time for looking at things that are in the 8 hours direction. What constellation does that correspond to? Gemini. It's a good time to see Gemini in January, because that has a right ascension of around about 8 hours, and it's going to be crossing the meridian at midnight. Right ascension, lines of right ascension, then you can think of as like a sidereal clock in the sky. It's just telling you which line is passing the meridian is the sidereal time. So let's have a look. Oh, got a black hole there. Look. That's interesting. So let's have a look at our sunrise and set diagrams that we saw earlier, but this time overlay this really useful grid line that you can imagine in the sky when you're outside. So we're back on the March equinox at sunrise, and solar time is about 6 hours, 6 hours 30. Sidereal time, we said it's 12 hours out of sync, and you can tell that because look, there's the meridian, the north-south line, and about 18.5 hours is the line that's crossing the meridian at that point. So sidereal time and solar time out of sync by 12 hours. And the lines of right ascension move in the same way that anything in the sky moves. They move from left to right for an observer in the northern hemisphere. So these imaginary lines are just going to move across the sky from left to right throughout the course of the day. Remember, we said that the sun is in the direction of 0 hours on the spring equinox. So there it is, you see, it's bang on 0 hours, and it's also on the 0 degrees line of declination. It's where the celestial equator crosses the ecliptic on March 21st. If we switch off the atmosphere, we can have a look at what some of the stars that would be in the sky that we won't see at that time of year because it's daylight. There's Altair, Arcturus, Vega, Deneb. So there's our summer, what we call the summer triangle, which is a collection of 3 stars in different constellations actually. But at this particular time of year, it's quite high in the sky when there's the sunrise. So we'll probably see it a little bit for a few hours before sunrise, but not in the evening. Let's move to noon. That line there is showing the ecliptic. I don't know if you can see that line. That kind of light purple line, that's showing the ecliptic. So at noon then, solar time about 12 hours, sidereal time now about 0 hours. These lines of right ascension have moved across the sky. The 0 hours right ascension is now crossing our meridian, so it's 0 hours sidereal time, 12 hours solar time. Switching off the atmosphere again, we can see Orion is actually just starting to rise at noon. We won't see it, but there it is. Orion is actually rising at about noon, but we won't see it at that time of the day because the sun's in the sky. If we move on to sunset, the line of 0 hours where the sun is now setting, and the line of 6 hours is now high in the sky. Orion is there, so Orion is actually in the sky at sunset. So we'll probably see Orion at this time of year for a few hours after sunset. There it is, visible for a few hours after sunset. Moving on to June, the sun is now, as we said before, rising much further north, and the reason for that is because it's now on a declination of 23.5 degrees. It's higher in the sky. The line of 0 hours declination is still rising due east and setting due west, but the sun is now no longer on that line. It's moved on the ecliptic to a higher declination. That's why it appears to rise at a further north location. Switching the atmosphere off again. And then at noon in June, there's Orion high in the sky with the sun. That's why we're not going to see Orion in June, because it's high in the sky when the sun's high in the sky. It has a right ascension of 5 or 6 hours, and the sidereal time at noon is about 5 or 6 hours. Solar time is about 13 hours. So there we go. Orion is high in the sky at noon, but not observable at night. Moving on to sunset. We've said here that in June, sidereal time is out of sync by 18 hours, but if you look at this, if you can subtract 14 from 21, that's actually not 18 hours, is it? It's the reason is because we're on daylight savings time. So true solar time at this point is 20 hours. Is that right?
Yeah, it's 6 hours.
So 6 hours behind, yeah. So 20 hours solar time, sidereal time 14 hours, 6 hours difference. Switching off the atmosphere again, see what's behind. You can do things like that on Stellarium. I was going to show some animations on Stellarium, but I think we don't have time for that. September equinox. Again, we're back on the celestial equator with the sun, so it's rising due east and setting due west. But now, if we switch the atmosphere off, we can see Orion high in the sky at sunrise. So we're going to see it for a little while before sunrise. Noon and sunset. Moving on to December, which is moving on rapidly, unfortunately. You can see now sidereal time and solar time are out of sync by 6 hours. So we've got 8 hours solar time in the morning, sunrise, and we've got a sidereal time of about 14 hours. Okay? And we won't see Orion at all now because it's at 6 hours. It's on directly the midnight side of the Earth, so we're going to see it about midnight. There's another little sidereal time demonstrator which shows position of a star in the sky. And you can see this, we can change the right ascension and declination, and we can change the corresponding sidereal time and latitude of the observer and see where that star would appear. So you could use a little animation like this to say, set your declination and right ascension of an object that you want to look at. It'll give you a nice graphic as one, whether you'll be able to see it at your latitude, and two, whether you can see it at a particular sidereal time. So let's just summarise then the factors that affect what we see in the sky. First of all, we looked at the observer's latitude, which determines which objects rise above the observer's horizon and by how much. Secondly, the time of day and the time of year, which taken together define sidereal time. Those factors determine the current position of the celestial sphere. So you can either think of time of day and time of year combined, or you can think of a single parameter, sidereal time, which tells us the position of that imaginary sphere in the sky. And we've said that objects are highest in the sky when the sidereal time equals the RA of the coordinate of the object that you're looking at. So if you want to look for something which has a right ascension of 3 hours and 15 minutes, the best time to view it is going to be at a sidereal time of 3 hours 15 minutes. And hopefully from that you can see how very useful this idea of sidereal time is, because it just tells you where something's going to be in the sky if you know its right ascension coordinate. So in order for an object to be visible then, the following conditions must all be met together. The object's declination coordinate must be such that it rises above the horizon for the observer's latitude. It must actually be above the horizon at some point. The sidereal time must be such that the corresponding line of right ascension is currently above the horizon. And the sun must be below the horizon when the right ascension of the sun is similar to that of the object to be viewed. So the sun must be below the horizon at that point. So it will not be visible at that time of year. Here's the sky seen from our kind of latitude. If you imagine that you lay on your back and look up at the night sky. Pardon?
I think you get wet through.
You get wet through tonight, yeah. Imagine on a dry night, you lay on your back.
Dry night, yeah.
You go to sleep. I remember one of those as well, dry night. But it was going to be, what you're going to imagine that you can see the North Celestial Pole offset. It's not going to be directly overhead. It would be if you were at the pole, and it would be on the horizon. So this is the kind of view that you're going to see. And looking towards the north, you're going to see objects move counterclockwise. Looking towards the south, you're going to see objects rise in the east and set in the west, moving left to right across the sky. And the celestial pole is offset to the horizon by an amount depending on how far we are from the pole. Which stars we see at our latitude is determined by the time and date, we've said, which is the sidereal time. And that's introduced now something called planispheres. Don't know if any of you have seen one of these, but it's a nice little way of calculating what stars we can see at a given time of year and a given time of night, or alternatively what we're actually doing is just setting the sidereal time. So that view that we see there is just the same kind of view that we saw back there for a given latitude. Here's another one, which they call a star wheel, but it's the same thing. Notice that the month increases clockwise around the planisphere. Here's an interesting one. I wonder if it's a faulty one.
Southern.
That's right. Why on this one would the month be increasing counterclockwise? And the answer is simply because this one's for use in the southern hemisphere. And the sky appears to rotate the opposite way in the southern hemisphere. So all the months go the opposite way around the dial to compensate for that.
If anybody offers you a batch of
Anybody offers you a bunch of planispheres, have a look which way the month increases. So you've either got to reject them or move to Australia. Tracking the sky then with telescope mounts. We want to put our telescope on a mount which enables us to track any object across the sky, to move and point to any object in the sky. Now an object like a mount like this is what we call an alt-azimuth mount, because it can move in altitude, that is up-down, and azimuth, which is left-right. So we can point to any point in the sky by moving up and down a bit and left and right a bit. Although straight up would be a little bit difficult on that mount.
About 45 degrees.
Yeah, I think so on that one, yeah. It's an animation, it's bear with me.
tripod.
Yeah. So the thing is, if you used a mount like this at the pole, you could track the sky by just moving in one axis, that is the azimuth axis. Because the whole sky appears to rotate around the North Celestial Pole, which would be directly ahead at the pole, we'd only have to move in one direction to track an object across the sky. Now, wouldn't it be nice if we had that advantage of moving in only one axis at any latitude? And the way that we do that is using something called an equatorial mount. And all an equatorial mount is effectively the same kind of mount with the vertical axis tipped over so that it points to the celestial pole. So we can now track any object in the sky by moving around the right ascension axis. So the advantage of that axis, the advantage of that mount, as we say, is it just enables us to use a single movement in one direction to track an object across the sky.
Well,
Now, practically speaking, a real equatorial mount has to be able to be adjusted so that its polar axis can point to different angles so that you can use it at different latitudes. You can see that that one there that Jed's brought down, there's an adjustment of the polar axis. And that polar axis is actually going to vary the direction depending on our latitude. Here's a picture of a telescope in an observatory somewhere, and you can see it's on an equatorial mount. It has a polar axis, or a right ascension axis, and a declination axis, which allows it to be moved in both directions. Now, if I were to ask the question at what latitude that observatory is, how would you know? By the angle of the polar axis, that's right. So here's the clue. If you see a telescope in an observatory, you might not know where it is, but you've got a very good idea of what latitude it's at just by looking at the angle of the polar axis relative to the horizon. A good one in a quiz question, if you get an observatory question, you just say, where's this? At least you'll know the kind of latitude it's at by looking at the angle.
North or south, though?
Pardon?
North or south, though?
You don't know north or south, that's a very good point. So the answer is it's 40 degrees.
Unless you know...
North or south, but we don't know. We can't tell from that. is actually the Washington Observatory in St. Louis, Missouri. That's the Yateman refractor. There's another one. Here's a guy with a very big looking telescope. He helped discover an Earth-like exoplanet fairly recently. What latitude is he located at? Well, how do we know? We look at this angle again, 32 degrees. So he's at 32 degrees north or south, we don't know. He's actually near Perth in Western Australia at 32 degrees south. And there's a little link to the article in case anyone wants to follow it. By the way, I'll try and put a link to this. I'll try and see if Mike wants to put a link to this presentation on the website, so that if you want to take a look at it, you'll be able to do so. So there's the kind of stylized picture showing an equatorial mount on the Earth, and you see we always set them up so that the polar axis is parallel to the axis of the Earth, and you can see from that as we vary our latitude, that angle is going to change. At the pole it's going to be straight up, at the equator it's going to be lying flat. Setting circles then. Setting circles are on a lot of equatorial mounts, and they're just a couple of dials around the two axes of the telescope, which are marked in hours and minutes in one direction and declination degrees in the other direction. There's two methods of using these. One is, which you find to be the method that's usually spoken about if you look up how to use setting circles. You find a reference star, you find a bright reference star, you point the telescope to that, and then you move the right ascension circle on the telescope so that it corresponds to the right ascension of the object that you're looking at. You can then move the whole mount around so that it's pointed to the right ascension of the object that you want to look at. But of course, to do that, you have to find a reference star and know its coordinates. Another way of doing it, which would just give you the right ascension setting, would be to align the right ascension circle so that the current sidereal time is pointing to the meridian. So if I've got a mount like that, which is pointing to the north celestial pole, the opposite direction of the mount would be due south. And I know that if I line the right ascension setting circle up so that the current sidereal time is matched up with due south, I can then move the whole mount in right ascension, and it should point to the object that I want to look at. Never trust a man that says should. That right ascension circle has two sets of numbers. Again, Y, it's pretty obvious, one for each hemisphere. So you'll see a lot of telescopes have sets of numbers run in the opposite direction so they can be used in both hemispheres. So the final topic that we'll probably cover is an idea called procession. What is procession? If you've ever seen a gyroscope and set it spinning, you'll see that it wobbles like that. The axis of rotation moves around another axis. Well, the Earth's axis also precesses, but over a much longer period of time. It takes about 26,000 years for the Earth to wobble once and point to the same direction in the sky again. Right now, the North Celestial Pole is very close to the star Polaris in Ursa Minor, which makes it quite handy for lining telescopes up. But it's not always been that way, and it won't always be that way. Celestial pole, the position of the celestial pole, is going to trace out a circle over about 26,000 years. So here we are a little bit after AD 2000, so we're probably a bit closer to Polaris than we were in 2000. 13,000 years from now, apart from the fact that the stars would have moved a bit by themselves, but the North Celestial Pole will have moved over there, somewhere more near Vega. Maybe not very close to Vega. But not only does the position of the celestial pole move, but of course our declination coordinates move with it. The whole reference system that we use is based on the Earth's spin. So as the Earth's direction of spin changes, so our declination coordinates change. 13,000 years, Polaris will be about 43 degrees north, because we said that this distance from the pole star to the ecliptic pole is about 23.5 degrees. Double that is 47 degrees, and subtract that from 90, you get about 43 degrees.
And you start arguing with an astrologer.
Indeed, yes. So, we've said that the position of the celestial pole moves, but also the position of 0 hours right ascension also moves, because, for the same reason. So that's moving westward throughout the sky. We said earlier that the what we call the 0 hours of right ascension was also called the first point of Aries, because when the constellations were defined it was in Aries, but now it's not. It's shifted to the west. It's now in Pisces. So there's our grid system with 90 degrees declination near to Polaris and 1 hour right ascension that way. 14 hours right ascension, 13 hours right ascension kind of down and that way through the Plow. As the Earth precesses, not only does the position of the pole move, but also the right ascension moves. So the right ascension coordinate kind of moves around and the position of the pole moves around. So now 1 hour is going to be that, I say now, like 7,500 years from now. The North Celestial Pole, declination 90 degrees, is going to be somewhere there, but that direction is now going to be 1 hour, whereas previously it was kind of that direction. And again, moved around again, 1 hour is now that way. Plow is going to be probably at about 21, 22 hours right ascension, as opposed to about 12 hours that it is now. And then it's going to move around a bit more. So a quick review then. Sorry to have probably gone on a bit longer. To map the sky, we imagine that all objects are fixed to a celestial sphere which rotates about the Earth once per sidereal day, which is a little bit shorter than 24 hours. Or we can call it 24 sidereal hours. The grid system is overlaid onto this imaginary sphere with lines of declination and right ascension. Declination has units of degrees and corresponds numerically to terrestrial latitude. Right ascension corresponds to terrestrial latitude, but it's divided into 24 hours rather than the 180 degrees east or west that we use for terrestrial longitude. Hours of right ascension correspond to sidereal time. The 0 hour reference for right ascension, if you like the celestial sphere's prime meridian, is defined where the ecliptic crosses the celestial equator on the March equinox. Sidereal time defines then which line of right ascension on the celestial sphere is currently crossing the observer's meridian, and it gains about 4 minutes per day relative to solar time. Our coordinate system then is not based on any specific object in the sky, because everything's moving relative to everything else, but our coordinate system for mapping the sky is based on the Earth's rotational axis and the point where the ecliptic crosses the celestial equator from south to north. And it's because the Earth's axis precesses, so the coordinates of all the objects in the sky change. Not only are the coordinates of objects changing because they're moving in their own right, but also because our grid reference system is constantly shifting, albeit very slowly. So terminology we've learned tonight: celestial sphere, right ascension. If we've got more time, I would ask you to define these. Anyway, declination, ecliptic, hopefully you should know what all these terms mean now. Altitude and azimuth, meridian, the zodiac, nothing to do with astrology, I hasten to add. Solstice, equinox, first point of Aries, which is actually in Pisces, and the first point of Libra, which is the opposite equinox, which I think is in Virgo. Anyway, it's not in Libra. We know what a solar day is, we know what a sidereal day is, we know what sidereal time is, and we know what azimuth mounts are and equatorial mounts. So I was hoping to show how to set up the setting circles, but I think we're probably going to get kicked out soon. So this presentation, in case anybody's interested, I'll upload it to that location. I'll see if Mike can put a link on the website, possibly. Watch it again. You will need to download Flash Player if you want to view this to play with animations, but if you don't, they'll just show us still images. You get the main part of it. This sidereal clock that I've had running is also a free download from that location. And thank you very much for your attention.
Thank you very much. Any questions, anybody?